Now we'll discuss the problems in the second assignment. The first problem is given here. It's a nonlinear device whose characteristics are given here. Okay. It has some I2 given by this expression. It depends on V1 and V2, and I1 is simply I2 divided by some constant. Okay. So how do we go about solving this? You're asked to find the small signal Y parameters at the operating point. Okay. And the operating point is given as I2 being 6 milliamps and V2 being 5 volts. Okay. So from this equation we get 6 milliamps is Is exponential V1 by Vt 1 plus V2, which is 5 volts, divided by Va, which is 25 volts. This number is 1.2, so this number has to be 5 milliamps for this equation to be satisfied. Okay, so from this we can get everything, right? So y11 is nothing but partial derivative of I1 with respect to V1, okay, which is 1 over beta partial derivative of I2 with respect to V1, because I1 and I2 are related by this constant beta. And this, if I differentiate this expression for I2 with respect to V1, you would get Is divided by Vt exponential V1 by Vt 1 plus V2 by Va. Okay, and you can see that this whole thing is nothing but I2 itself. Okay, so you get 1 over beta times I2 by Vt. Okay, and y12 is partial derivative of I1 with respect to V2, which is 1 over beta partial derivative of I2 with respect to V2, which again differentiating this expression with respect to V2, you get Is exponential V1 by Vt 1 over Va. Okay, and if you want to calculate y21, it will be partial derivative of I2 with respect to V1, only this part of it, that is this without the beta. So it's I2 by Vt, and y22 similarly is the same expression without this beta, Is exponential V1 by Vt divided by Va. Okay, now I can substitute all the numerical values and find the answers. Okay, so for y11 we have 1 over beta, which is 1 by 40 times I2 by Vt. I2 is 6 milliamps and Vt is given to be 25 millivolts. Okay, so what does this give you? This gives you 0.006 Siemens or 6 millisiemens. Okay, and y12 is this, which is 1 over beta, which is 1 by 40, 1 over Va, which is 1 by 25 volts, times Is exponential V1 by Vt, which we know is 5 milliamps. Okay, and this is 0.005 millisiemens or 5 microsiemens. Okay, coming to y21, we'll have I2 by Vt, which is 6 milliamp by 25 millivolts, which corresponds to 240 millisiemens, and y22, which is this quantity, which is 5 milliamps divided by Va, which is 25 volts. This is 0.2 millisiemens or 200 microsiemens. Okay, so the Y parameters of this nonlinear circuit at the operating point are 6 millisiemens, 5 microsiemens, 240 millisiemens and 200 microsiemens. Okay. In this problem, you are asked for identifying transistors which are in triode region. Okay. Now we know the condition for the transistor to be in triode region. VDS must be smaller than VGS minus VT, or sometimes it's easier to compare the drain voltage to gate voltage, or you could say that VGD must be greater than VT. Okay. And in some cases currents are given. Now how do you identify it in that case? You know that ID VDS characteristics look like this. There is a parabolic increase and then a flat region, and this is the saturation region where the current is independent of VDS. Now the current can be either equal to the saturation current or less than that. It can never be more than that. So for instance, in the first case, when you are given VGS and the drain current, you calculate the saturation current for this level. If the current is less than that, it has to be in triode region. Okay. So let's go over all these cases quickly. In the first case, VGS is 3 volts, and if you calculate the saturation current, it will come out to be 200 microamperes, but the actual current is 150 microamperes, so this is in triode region. That is, this level is 200 microamperes and it's operating somewhere over there. Okay. In this case, it's given that the drain current is 200 microamperes and VDS is 2.5 volts. Now if it is in saturation, we don't know that yet. For a 200 microampere drain current, you evaluate that the VGS has to be 3 volts. Okay. So if VGS has to be 3 volts, then you can see that VDS, which is 2.5 volts, is greater than VGS minus VT. So this is in saturation region. Okay. Now in this case, you are directly given the value of VDG. VDG is minus 0.5 volts, or VGD is 0.5 volts, and this condition is not satisfied. So this is also not in triode region. The third case, we are given something here. We have a VGS of 3 volts and the drain current is given to be 450 microamperes. Actually this case is not even possible. Okay. And here we have a VDS of 3 volts and a drain current of 50 microamperes. For a current of 50 microamperes, if it's in saturation region, this will be 2 volts and VDS is greater than VGS minus VT. So this is in saturation, it's not in triode. In this case, VGD is given directly. VGD is 1.5 volts in F. So clearly it satisfies this condition. So this is in triode region. Okay. And here you are given VGS and VDS. Clearly VDS is more than VGS and it satisfies the saturation region condition. And here it's the opposite. VDS is 2 volts and VGS is 4 volts. So you can easily see that this condition for triode region is satisfied. So this is also in triode region. Okay. So A, F and H are in triode region. Okay. And in this case, you are asked for cases which are impossible in any region of operation. Okay. So that we had already identified. If you have 3 volts of VGS, the saturation current is 200 microamperes, and here a current of 450 microampere is indicated. Okay. So this one is not possible at all. So D is the correct answer. Okay. In this problem, you are told that if you use a MOS transistor between the source and load, that means that we ignore all the biasing arrangements and assume that the MOS transistor is connected like this. Okay, where this is VGS and that is GM VGS. So the gain is just minus GM RL and that should be minus 8. The gain magnitude is given as 8. So clearly GM has to be, if you calculate it, it will come out to be 160 micro Siemens. Now in saturation, this is equal to mu n Cox W by L times VGS minus VT, and from this you find that VGS minus VT is 1.6 volts because this part is 100 microamperes per volt square. Okay, so because VGS minus VT is 1.6 volts, the saturation region current ID, which is mu n Cox W by L 1/2 VGS minus VT squared, this will come out to be 128 microamperes. Okay, so that's the question that is asked. Determine the bias current which must be flowing through the MOS transistor. Okay, and the answer is 128 microamperes. So the next one is sort of continuation of the same. You are asked to use the bias point from the previous one. So that means that this transistor is biased at a current of 128 microamperes, and this voltage VGS minus VT is 1.6 volts. So this is 2.6 volts. Okay. And you're also told that the drain bias resistor is the same as the load resistor. So this is also 50 kilo ohms. Okay. And VDS is VGS plus 1 volt. So VGS is 2.6 volts. So VDS, this point here, must be at 3.6 volts. Okay. So now let's see. It is also given that the current through R1 and R2 must be 10 microampere. To find out the current in R1 and R2, you need to know the supply voltage VDD. Okay, how do you calculate that? You know that this is 50 kilo ohm and a current of 128 microamperes is flowing through that. So the voltage drop across RD is 6.4 volts. Okay, so the 6.4 volts plus 3.6 volts of drain to source voltage of the transistor give you a VDD of 10 volt. Okay, now if 10 volts is applied across R1 and R2 and the current through R1 and R2 has to be 10 microampere, then it tells you that R1 plus R2 is 1 mega ohm. And how do you find the individual values? You know that across R2 you need to have 2.6 volts. Okay, so from this you can easily calculate that R1 is 740 kilo ohms and R2 is 260 kilo ohms. Okay. So first of all, the supply voltage VDD, that's the first part of the question, that is 10 volts. And you have to calculate the small signal gain V0 by Vs, and assuming that capacitors are very large, which means that they are really short circuits. Okay. So the incremental picture, assuming that capacitors are shorts, look like this. 100 kilo ohms, and you have R1 and R2 in parallel with each other. One of them is 260 kilo ohms and the other one is 740 kilo ohms. Okay, and we have GM, which is 160 microsiemens, and we have RD, which is 50 kilo ohms, and we have RL, which is also 50 kilo ohms. Okay, so very easy to solve for this. So V0 by Vs will be, first of all, there is a voltage division between these two. Okay, so this 260 kilo ohm parallel 740 kilo ohm, this will come out to be something, I'll call it Rx. Okay, so V0 by Vs will be Rx by 100 kilo ohm plus Rx times the voltage gain from this VGS to the output will be minus GM times RD parallel RL. Okay, the voltage here will be times VGS. So this is the gain, which comes out to be minus 160 microamperes times 50 kilo ohm parallel 50 kilo ohm, which is 25 kilo ohms. Okay, so this part will be minus 4 and this part will be less than 1. Okay. and if you do all these calculations, you will get the answer to be minus 2.63. Okay. So this is first of all some practice in solving this type of problems. Also you can see originally we started with the value of GM such that GM times RL is minus 8. Okay. Because of all these biasing constraints and so on, it has come down to minus 2.63. Okay. Of course, if we had chosen R1 and R2 to be higher, then it wouldn't go down to this level, it would go down to minus 4. But still the gain will reduce because of the presence of these extra components. Okay. Next you have to find the constraints on capacitors. So first you are asked for capacitor C1 and then C2. Okay. So you know that 1 over omega C1 must be much more than Rs plus R1 parallel R2. Okay, and omega is 2 pi times 10 to the 4 radians per second. Please do not confuse between hertz and radians per second. Okay, this omega is 2 pi times the frequency in hertz. Okay, and if you evaluate this, you will get C1 to be much more than, if you evaluate this, C1 has to be much more than 1 over omega times Rs plus R1 parallel R2. This is 54 picofarads. Okay. Now what value do you really choose for C1 in a circuit? Maybe 10 times this or 20 times this. That is, you would choose, let's say, 540 picofarads. And also there are standard values of capacitors that are available. You choose the nearest standard value, or you round it up even further and maybe use a 1 nanofarad capacitor. Okay. And for this output coupling capacitor C2, the constraint is C2 must be much more than 1 over omega times Rd plus RL. This is the constraint so that the transfer function with the capacitor shorted and with the capacitor in place are almost the same. Okay, and this comes out to be 159 picofarad. Okay, that is, you will choose C2 to be about 10 times higher or 20 times higher. If you choose 10 times higher, 1.6 nanofarad will do nicely. Okay. Now there is another possible constraint where the drain voltage has to be equal to the output voltage. In that case, C2 has to be much more than 1 over omega times RL. Okay, and this will come out to be exactly double that one. Okay, which is 318 picofarad. So in this case, this constraint is double that one, and in reality you may use C2 to be about 3.2 nanofarads or so. That is 10 times that one. Okay. So because it's an inequality, the exact value of this is not important. Maybe you can use 4 nanofarad or something like that. Okay. Now, so far we are used to looking at circuits with AC coupling at the input and output. In some cases you may want to avoid it because the input signal may itself have a frequency that is very low or even zero, that is DC. You could expect DC increments. In that case, you clearly cannot use capacitors. Sometimes when the frequency becomes very low, it could be that the capacitor values become so large that they become impractical. Okay, so this is one such possibility. But usually whenever you have such a condition, you will end up having to use two supply voltages. A single one will not do. You have to use two of them. This is known as dual supply. Okay, and the midpoint here is grounded. Now what is it that is asked for? You are asked for the value of Rd such that the quiescent output voltage is 0. Okay, because earlier we had a quiescent output voltage which is non-zero, we had to use a capacitive coupling to eliminate that. Now if it is 0, we don't need to do that. We can take the output directly between the drain and ground. Okay, how do you calculate this? In the quiescent condition, Vs will be 0 because Vs is just a signal. So in the quiescent condition, the gate is at 0 volts and the source is at minus 3 volts. Remember, this is at 0 volts, so this is at minus 3 volts. So the gate source voltage is 3 volts. Now I want the transistor to be in saturation, and if you calculate it from these constants, the drain current comes out to be 200 microamperes. Okay, and this voltage is nothing but, this is 3 volts here, that is 3 volts minus 200 microamperes times Rd, and that should be equal to 0 because the quiescent output voltage must be 0. So Rd is 3 volts divided by 200 microamperes or 15 kilo ohms. Okay, so that's the answer. So if you have RD equals 15 kilo ohms, this point will be at 0. Now the next question asks for small signal gain V0 by Vs in the previous case. Okay, now I assume you can easily evaluate the small signal equivalent of this at a drain current of 200 microamperes, and that is equal to a GM of value 200 microsiemens. Okay, this is VGS. The rest of it is the same as before. We have 15 kilo ohms going to ground in the incremental picture. Remember, in this particular case, these are fixed voltages, so this point is ground in the incremental picture, this point is ground in the incremental picture, and of course these 2 points are already designated to be grounds. And the input is applied through a 100 kilo ohm resistor. Okay, in this case there is no voltage division at all because there is no resistance between the gate and ground. So VGS will be equal to Vs, and the output voltage will be minus GM RL times Vs, which is minus 200 microsiemens times 15 kilo ohms times Vs, or minus 3 times Vs. So the small signal gain is minus 3. Okay, so that brings us to the end of the second assignment. Hopefully you have been able to solve all the problems, but if you have not, please go back and solve it step by step, making sure that you understand every step of it so that you don't repeat the same mistakes in the future. Okay.